So, C3H8O, one of the reasons why this one's going to become a little bit more challenging is that we could go through our basic kind of rule set, total it up, carbon 4, 3, gets us 12, hydrogen 1 times 8, oxygen 6 times 1 equals 6. Yeah? 26, thank you. Said math. Okay, and now the real challenge is how do we then draw the structure out? Okay, well, so here's how you should have drawn it out. I might come back to you in a second to repeat that, just for future posterity's sake for the recording. What did you say as I was drawing that?
So that's just mean.
Oh, okay. How many people got that? Feel free to take a look around and see hands. Oh, that's interesting. What the heck? Why'd you not get that? What's an H? How many people got that? Whoa. So who was right, red or purple? Both. Formulas are pretty horrible ways to represent a compound. You remove so much information about the structure and ultimately its reactivity that providing a chemical formula is next to meaningless. Okay? The red compound has virtual no reactivity. The purple one has a significant amount of reactivity. We're doing a drastic change in the chemical properties of these compounds, but we're going back to the exact same formula. Formulas are bad, don't use them. Okay? You might say, well, then why'd you do it? Right? Fair enough. I did it to draw attention to the fact that formulas are bad and that you shouldn't use them. Okay? So you can use them in the context of saying, this is a dumb idea, you shouldn't do this. That's the only time you're allowed to use formulas. Make sense? Okay. So what we want to do is adapt our formulas to be better representations of the ultimate structure. One way to go through and do it is to always provide the Lewis structure. Why would we have written a formula and not the Lewis structure?
Simplicity sake.
Simplicity. The formula is a hell of a lot easier to write than the structures. Okay? Take this a step further. How is most of our thought transmitted from one person to another?
Writing.
Through writing. Writing on what instrument?
Computer.
Computer. Or a printer. Or not, that's not what I meant to say. Typewriter. Okay? Where this ultimately came back from. And you're like, typewriters? Think historically. Right? It's still the same origin. Can I, on a computer, draw out those structures that easily? Okay? And we're starting to achieve this area of like, that's not that hard, dude. Like, you did it literally on the screen. Yeah, we're reaching a point in technology where writing out the structures is now becoming very, very easy to do. Okay? Which is then going to make writing out chemical formulas kind of a thing of the past. We aren't there yet. We're transitioning. Okay? So what you end up being responsible for is that lovely transition time. You're responsible for being able to interpret how does a formula make it into the structure. We can't give you this formula and just say, provide the answer, because there isn't one answer. In this case, there's 3 answers. Okay? All of them equally valid. So how can I change the formula to better represent that I want you to give me the red answer and not the purple answer? like that. Okay, so we're coming up with ways to split and adjust.
CH3, CH2, OH, CH3. Or no, sorry, O, CH3. Yeah.
Okay, so what we're doing is breaking down our formula from our structure. This formula makes a lot more sense. Even then, we've hidden a lot of information behind the structural characteristics found in the formula. Okay? We're sacrificing that because I want to type it. Okay? Most of what we do is not typed. It's handwritten stuff, which means most of what you want to do is those Lewis structures. That's where you want to exist. Okay? How do you know to go from the formula to one of those Lewis structures? Okay? Quickly and efficiently. For instance, even if we drop to this one, okay? How many of you attempted this one? I know at least one student has attempted it. Okay, a couple people. So let's go through and take a look at that one. What makes that one a little bit more difficult?
You didn't provide the charge for the cation.
I didn't tell you what a cation was. Sneaky little underhanded jerk that I am. CH3, yeah. CH3O, cation would be positive. So carbon, 4, hydrogen, there's 3 of them, 3, oxygen, 6. The cation means -1, so we get a total of 12. Okay?
Should we just assume when you see cation without charge specified, it's always -1? Because it might not be -1.
So let me restate what I heard. Should we assume that whenever we see a cation, we should -1?
No. When we see cation without a specific charge. So like.
I think I see what you're saying. Without a specific numerical value attached to it.
Right, like
Yes,
I see
you should
cation.
assume singles. Okay? And one of the things that we'll find when we go through and evaluate our structures, if we see larger than single charges, that's usually a red flag. What we drew was wrong. We screwed something up. Okay? Most of the time, our charges are going to come in as single values. Okay? It's very rare to see multi-charged structures, at least at this level. Okay? So what should we do? We now know how many electrons. How do we put it together? Pick a central atom. Carbon's a fantastic central atom. Follow up on 2 pieces of words or 2 students' pieces of information. We follow the rules that Mike gave us because he's the instructor and of course he's brilliant. Let's prove how awesome that statement is. Okay, now what do? We got 12 electrons. We need to place our 12 electrons. I'm going to start placing around the oxygen first until I achieve an octet. Then I'll go around the carbon until I have my 12 electrons. Did I count 12?
No, he's down to 14.
I put 14. Okay. That should scream problematic because
There's no electrons in the hydrogen.
I don't have a bond there. So let's see what we can do to fix that. What does that mean needs to happen?
That hydrogen is going to be removed.
Not necessarily.
You're going to need to steal electrons from oxygen.
I have to take electrons away from the oxygen to make sure I have that bond to that carbon. Whoops. All right, now I've got all the bonds put into the structure. Does this represent that formula? Does it have all the atoms? Does it have the proper number of electrons?
You didn't put the formal charge on the oxygen.
Did I say it was a good drawing? Okay. All I asked is, does this satisfy our minimums? Yeah, we should finalize this. Okay, and our final step in OCHEM is assigning formal charges to all of our atoms. When we go through and assign formal charges, what are we going to find happens? The oxygen is going to come in as charged. Oxygen has 6 valence electrons minus the number of non-bonding electrons, 4 minus the number of bonds, 1, and we get a positive charge. right? And you might be screaming, well, that's horrible now. I would argue that we should have said it was horrible before then. What is the problem with that structure? We don't have an octet on the oxygen. That doesn't make this an invalid Lewis structure. This makes it not a good one. Okay? Is there a better representation for it? Okay, so not having an octet on the second most electronegative atom on the periodic table is probably a bad idea. Okay, so maybe the arrangement of atoms I picked was incorrect. You should immediately outright and say, hell no, stop drawing it, because hydrogen can't have 2 bonds, it can't exceed its octet, which is only 2 electrons. Why is hydrogen not an octet?
Because it's on the first column of the periodic table.
First row of the periodic table can hold how many electrons?
2.
2, and only 2. There's no place to put those extra electrons to make that second bond. So that is an invalid representation. I'm going to have to maintain that. I had all of the hydrogens around the carbon to begin with, so maybe I was wrong and they should have been all around the oxygen. Okay, how many electrons are drawn in there? I know that looks like a double bond. I apologize. Fixed it.
4.
Okay, we've got 8. How many electrons do we need? 12. There's my 4 more electrons. All right, so we're getting, no, you can't do that. Why? Carbon's missing its octet. Well, we had oxygen missing its octet versus carbon missing its octet. Which one's better?
Carbon.
Carbon. So we went all the way to formal charge with the red one. What should we do with the purple one?
Do formal charge.
Oh, God. Really? Yes. Okay. Carbon has how many valence electrons? 4 minus 4 minus 1 gets me a negative 1. This should be screaming problematic at you because I wanted a cation, and I've now dropped a negative charge in the structure, which is an anion. Okay, so we can move over to the oxygen. The oxygen has how many valence?
6.
6 minus
4.
how I've been doing it.
Oh, 0.
0
Minus 4.
minus 4 gets me plus 2. My negative 1 isn't necessarily all that bad because I've balanced it out. I still have an overall positive structure. It still matches everything. What is the problem with this one? No octet on the carbon and a lot of charge. Okay, not only a lot of charge, but a really high charge. So that structure is probably not good. Okay. This is one of the problems with doing massive just kind of mood swings. All the hydrogens were here. Well, I don't like that, so I'm going to put all the hydrogens over here. Okay? I would argue when you go through and do this process, you pick one, you start, and you go, oh, that was bad. I'm going to move 1 atom, not 3. Okay? And it's you can still end up at the same answer, but the methodicalness of moving 1 at a time is a little bit better. So let's go back and say, okay, well, I only wanted to move 1. How many electrons in the structure? 8. What do I need to do? Add 4 more. Where do I place those 4 more? On the oxygen. Why on the oxygen?
Because it's the most
The most electronegative element. That's why our electrons have to go there. Cool. Now what do I do?
There's a charge on
Draw
the
a
carbon
bond from
because it doesn't.
I'm going to argue we aren't going to look at formal charge yet.
Draw a bond from, take 2 of the electrons on
And
oxygen.
I'm going to argue saying drawing a bond is also not the correct place to start either. What is the reasoning behind why you want to do that?
By octet on carbon.
Octets. How many electrons are currently around the carbon? 6. It's missing its octet. Before I deal with formal charge, before I just start moving bonds, identify your error. The error is you're missing an octet. Because we're missing the octet, I can move those electrons, and now we can talk about it.
Now,
Now oxygen is missing this octet.
Okay, so when we talked about moving the electrons, what were we talking about the electrons being moved to? Into a bond between those atoms so that they could share those electrons. What we've effectively done there is generated a concept of resonance. That's what happens when you write over content. Okay? So what we're saying is I want those electrons located there. The difference between those two structures in black is only the location of, sorry, let me draw that other pair of electrons, the location of electrons. The atoms have all maintained their location, which means the relationship between those two black structures is resonance. Okay? Those of you like, that's a weird word, I hope I never have to hear that again. I'm not really sorry to inform you, that is organic chemistry, is resonance. You need to learn to love it. Okay? So those two structures are related only because we've moved electrons. Well, didn't I just move electrons here? Instead of the electrons between carbon and hydrogen, they're now between oxygen and hydrogen.
No, because you moved the electron, the atom, it's no longer bonded.
The atom has changed locations. So when we're talking about moving electrons in dealing with resonance, the atom can't change location. Okay? And that doesn't mean in the case of the purple one that I could do something like this. Well, now I haven't moved the location of the hydrogen. It's still in the same spot. I just made a really long, no, that's cheating. Okay? We've changed the connectivity of those atoms. Okay? So when I'm looking at resonance, what electrons might I be allowed to move around the structure? Non-bonding electrons are absolutely fair game to move. Because to go from that top black structure to the bottom, what did I do? I took this pair of electrons and I moved them there. Awesome, I love your suggestion. There's another answer. How do I go from the bottom structure to the top one?
So I take an arrow from that bond, the double bond.
I can go from that bond out here. So you're now saying I can move electrons from an atom to a bond or a bond to an atom. Going from the red structure to the purple structure, didn't I just move the electrons from a bond to an atom? What's the difference between the electrons that we're talking about on transitioning between red and purple versus in the black structures? What is different about this bond from this bond?
Double bond.
It is a double bond. Okay, and what we will learn, which in theory, again, 151 might have talked about, is that a double bond and a single bond are horrible terms. Okay? Multiple bonds means there's multiple sources of electrons to make those. If you have multiple bonds, you're allowed to move one of those multiple bonds. You cannot move the other one, because the last one would be a single bond, for lack of a better term. Kind of makes sense? Ish? We're trying to dodge by not using fancy terms. Okay? The fancy terms, sigma bonds, don't touch. Pi bonds, do whatever you want with, within reason. Okay? So now when we go through and look at the black structure, we said the bottom structure should be the better of those two because everything has a full octet. Since we've decided on a good structure, now what should we finalize with?
Formal charge.
Formal charge. And we go through and do the formal charge, we find that
Oxygen plus
the oxygen is positive. Just for giggles, if we went back to the top one that we drew out and did a formal charge, we'd find that the carbon is positive. Okay? This is where deciding best and useful comes into play. The best structure is the bottom black one. The most useful is the top black one. Okay? Why? What is oxygen going to do if it has a positive charge?
It's gonna make a bond.
If it has a positive charge, what is it going to do?
React with another compound.
To react with another compound, that other compound's going to have to come in and do what? What would that other compound have to supply to react with this positive charge? A negative. And a negative is electrons. Can this oxygen accept more electrons? How many electrons are currently around it? 8. Can it accept more? No. Is the oxygen going to react with another compound? No. It's a giant red flag that reactivity is sitting there, but it can't react outside the structure. If I can't get help from outside the system, where am I going to have to find help?
Inside the system.
Inside myself. Where do I find electrons to stabilize that positive oxygen? From the pi bond. Those pi electrons will come out and stabilize that positive oxygen, thereby making the carbon positive. This molecule will react how? An outside compound will come in and share electrons because it is a positively charged molecule. Where do those electrons react? At the carbon. Useful structure, because I can see how it's going to react. Best structure, because it's the best drawing.
So would the bottom be a major structure and the top one's
So the bottom ends up getting called a major resonance contributor, and depending on what course you're in, we tend to ignore this top one as a resonance. I would argue in OChem, as much as it kind of sucks, you can't ignore your best worst structure, because that's the one that's useful. Okay? Because it's the one that's useful, it's also going to be the one you use the most, which means when you get a test question asking which of these two structures is best, you're going to zoom in on the useful one. Keep in the back of your mind, useful and best are two different terms. Make sense? Questions? What do you guys think? Was that like an easy concept, hard concept? Okay, I can accept that. So we're getting a mixed bag. It's okay, because I haven't been forced to practice it too much. Okay? So, a couple things. We'll talk about the top part. Student evaluations from the past semester just came in. Is anybody interested in seeing what students had to say? Yeah? Okay. I'll copy those and make those available. I'm not going to bother to edit them, but I'll try and get them out there so you can see them. PlayPosit. This is what PlayPosit spits out, followed by all the student grades. So this is the Lewis structure PlayPosit for an older course. Okay? So when it comes to grading, the PlayPosits are usually worth 10 points. The Lewis video was an hour freaking long. Right? And if you've gone through and done it, you've probably seen your grade. And your grade, according to PlayPosit, was probably sub 50%. But I got every question right. There's something weird in how it does its grading. I don't even want to worry about it. So here's what I go through and do. You spent an hour watching the video. I think that deserves some points. 8 out of 10. You watched the video. The last 2, why would I pick 2? Because I look at this and I say question 6 and question 11 most people got right. The reason you got those questions wrong is probably because you were running out of time and you were just clicking blindly through the video. So you weren't paying attention to the video. That's fine. Right? You're still getting most of the points, but that's where I'm going to assign those last 2 points. You get them both right, 10 out of 10. You miss 1, 9 out of 10. You missed 2, 8 out of 10. Make sense? Okay. As far as whether or not PlayPosit acknowledges that you finished, when you finish the whole video, you should get some kind of completion screen. Take a picture of it. Upload that to Canvas. Right? You now have a record, a defensible record to come to me and be like, I already watched it. I don't care what your system says. Look, my name, assignment, completed. I don't have any choice but to give you points. Okay? Or a long, drawn-out fight through administration. Okay? Which I don't want to do.
Where would we upload that?
It should be within the Canvas. In Canvas, you've got the link out for the assignment. There should theoretically be a submit button. Because you're asking, I'm going to guess it doesn't say submit. Okay, I'll fix that. Okay. Minimally, if you screen capture it, you've got it for records, so if you wanted to challenge it, you could challenge it. Canvas will constantly tell you haven't done it, because Canvas and PlayPosit don't link. Because of how I grade the PlayPosit, it is insanely time-consuming. Okay? So my time to upload scores for the PlayPosit is horrible. Okay? I prioritize a hell of a lot of other stuff than that. Okay? Kind of makes sense? So if at any point you're concerned about PlayPosit, contact me. The point is, again, not for it to be a point of stress and contention, but a point to give you credit for having done that work. That's it. Questions? Cool. Hey, look at this. Resonance. Okay. Arguably with that last example, don't have resonance because of those two structures, only one of them was really good. The other one was missing an octet, so we run into this weird kind of gray area of saying, well, that's not really resonance. This compound fully has resonance. Okay? How do we deal with it? Okay, well, if you follow through the rules for how we would draw out this compound, we have CO3 minus 2. And we draw out all our stuff, carbon 4, oxygen 6 times 3, negative 2 charge means plus 2, we get 24. Carbon's our center, oxygen, oxygen, oxygen. We drop in electrons. 8, sloppy, close enough. 16. 24. So far, so good? Take that as a yes, because I'm trying to draw at the same time. And you didn't say anything. We still good?
Yes, we're good.
Okay. Do the oxygens have their octets?
Yes.
Does the carbon?
No.
No. So what needs to happen?
Electrons.
We need to take non-bonding electrons and share them with that carbon. Which non-bonding electrons? Any of them. They're all equally valid, which means you have 3 structures that you are required to draw to represent the compound. Okay? You are required to draw all 3 because any one of them is only a third of the picture. Okay? You could kind of envision it like taking a, not stop motion, but just taking a single screen capture, holding the frame, exposure on a camera open, with me constantly moving around the room. If you look at a single image, my arm may be here. Does that mean if you were trying to represent me, you would say Mike's arm is always upper right-hand corner? No, because at other times it's moving. The electrons are constantly moving, particularly those non-bonding electrons, particularly if there's another space that could use those electrons to satisfy an octet. Because they are constantly moving, we have to come up with a way to represent that constant motion. The way we do that is by drawing all of the possible structures. Taking a screen capture of me would really suck because we're saying, there's a unique drawing. There's the next one. And for those of you that are wondering what the hell I'm doing, infinitesimally small motions of my hand in a single direction. Doing it for a human being is really, really difficult because there's lots of possible states. There's a lot fewer possible states for a molecule. Okay? So we would end up having to draw all 3. Okay? One other option is to go through and be like, well, I'm going to draw the average of all 3 and say that really I've got electrons being shared all the way around this in what is known as a hybrid structure. Try and not say this insultingly. It's going to fail miserably. Hybrid structures are stupid. Okay? At no point will you use a hybrid structure for any reaction. Okay? That's using the blurred image of me moving my arm back and forth and trying to use that to describe how I'm going to shake someone's hand. Shake my hand. That makes no sense. Okay? So we would pick the image where it makes the most sense for me to shake someone's hand. Okay? And that's the image we work with. That's what we work with in OChem. We work with those freeze frames to say how this transitions through. The hybrid image showing the butterfly wings of my arms moving up and down, how the hell does that moth shake someone's hands? That's not useful. Does that make sense? Okay. So it's neat, it's pretty, go, oh, cool, lovely. Whoop-de-doo, I can't use it. Okay? And arguably it doesn't give me enjoyment because I can't use it. Okay? So the hybrid structure is a bad idea. Okay? Within that process, you at least saw how we got to multiple structures. Okay? They're a result of drawing Lewis structures appropriately. We run into an issue when we come to OChem. That issue is I start with this structure and I say, give me the resonance structures. You didn't have to walk through any processes to move through this. How do you know how to move to the other structures? Well, someone said, well, the double bond just needs to move. Why do you know the double bond needs to move? You're going to answer my question? You're going to suggest something different?
I was going to say why the double bond is moving.
So then no. Guaranteed, the reason why you think the double bond should move is because you know the freaking answer. You've seen this molecule a whole bunch of times. You're familiar with it. That's a crap explanation because that means you have to memorize all possible structures. That sucks for you. We need another way to represent and move between resonance structures. So what we can use is some of those rules that we figured out early on when drawing them out the long Lewis method way. What electrons were we allowed to move?
Bonds and lone pairs.
Non-bonding electrons and multi-bonds, best labeled as pi bonds. Can I move those electrons? No.
No. Yes.
Fair enough. Where do I want to move these electrons?
Make a pi bond.
What just happened to the carbon?
It's exceeding its octet.
It has now exceeded the octet. So you suggested, with some very easy manipulation on my part,
You would break the double bond with the
shh. You suggested that we should move these electrons there so that we can make a new pi bond. You just drew a structure that invalidated the octet of carbon. Your arrow pushing sucks.
We need another arrow.
Okay? And I'm going to argue no. Okay? You need to have a reason for why you're moving the arrow. To me, when you're saying you want that there, that's because you're saying you want a double bond there. You know the double bond appears to move. So I'm going to move it. That's the wrong fundamental underlying rules behind why you're making that motion. Okay? Before I see your hands, because I know I'm really trying to push at misconceptions on this. Okay? So if you got hands about like, but wait, why did you do that? Or why are you saying that's bad? I'll kind of accept those. What do you guys got? You want to give me more? Or are you saying, but no, it's okay? Okay, that's cool.
The why it moves.
Okay, so let's try something else. Because we're saying we're allowed to move those. Okay? And I said that was not a nice thing to do. Okay? So one of the other common ideas is, well, I know the double bond has to move. Already you've made a false statement. Okay? Because you're now making the statement, you're going into solving the question because you know the answer, you're going to make the structure do whatever you want it to do to make the answer. You can't do that. Okay? But here's another common thing. Well, the double bond shouldn't be there, it should be here. What would the result of that arrow be? Well, now I have the double bond there, right? Isn't everything lovely? What did I do to all of those electrons? I didn't touch them, which means, ooh, that still needs to be there. I've exceeded the octet on the oxygen. What did I do to the other oxygen? I took away its octet. So that starts to look like the bonding pattern is correct, but the electron pattern is off the charts, horribly wrong. By doing that very subtle, like innocent, well, it gets the same result. No, it doesn't. You've lost the understanding of how the electrons move. That's the problem. Okay? So we go all the way back to this, all the way back to the very beginning of this. Say, okay, well, there's no reason for me to move the non-bonding pairs of electrons, because if I move them, I exceed the octet on the carbon. Which means, should I move the non-bonding pairs? No. Don't touch them. What else are you allowed to move in resonance? The pi bond or a multi-bond. So we can take our focus up to our multi-bond, and I'm going to decide I want to move those electrons. Okay? Again, we just addressed that's a horrible, whoops, there it goes. That's a horrible idea. Okay, exceeding octet. Okay, arguably, we can't really move there. We're talking about where those red electrons can move. Can they move to the oxygen or towards the carbon? Why should they move to the oxygen and not the carbon? Oxygen being more electronegative suggests that those electrons should go up that direction. What's the result? The carbon's octet is unfulfilled, which means that structure is, and actually we don't even need to deal with the formal charges because I haven't done that yet. It doesn't yet. So no octet, which means this is a problematic structure. If I was going to compare these two, this does not count as a resonance structure because it is higher in energy than this one, because it doesn't have the octet. Can I fix carbon's octet? How?
Take one of the lone pairs, the non-bonding electron, and make it into a bond. There you go.
What structure have I now drawn? I now have a resonance contributor for the original one. I've shown all this gory, awful work in between pushing me through it. Okay? But I haven't exceeded octets. Being under octet is kind of wishy-washy okay. Over octets is really bad. Okay? Black to blue, I should never pass through the red because that's a bad one, which means I want to change the arrows that I add to my black structure so I never even hint at making it to the red one. What can I do? What is the combination of a red arrow and a blue arrow? I can entirely bypass the middle system. I don't have to go through and show that individual step. And I'm allowed to break it down with those two arrows. You should use the fewest arrows necessary to get to your next resonance structure. Why is that last one better than the purple one? It has an octet. Why is that last blue one equivalent to the black one? As a hint, it's not shown on either structure. Why are they similar energy? The formal charge. If we go through and assign formal charge for the black one, the two oxygens are negative. If we go through and look at the blue one, we still have two oxygens that are negative, but they're different, quote-unquote, oxygens. For those of you saying that we've done a rotation, resonance, the structure is pinned. Okay? You've dissected a frog and pinned it down. You can't rotate. Okay? Kind of makes sense? That is resonance. Really, really simply. On top of it, that resonance has now also established curved arrows. What were we moving with those arrows? Electrons. So an arrow now in organic chemistry is going to reference the motion of electrons. Not the motion of atoms, not the motion of bonds. Okay? It's referencing electrons, pure and simple. how many electrons were moved for a single arrow? How do you know it's 2?
Because it's a full arrow, not a half arrow.
The arrowhead is your hint. The arrowhead has 2 halves, right? 2 electrons. What happens if instead of moving 2 electrons, I decided to move 1?
Just a half.
It's now just a half arrow. Are we allowed to move just a single electron? Yes. You don't want to worry about it yet. We'll cram it in at the end of the semester. Like literally maybe a lecture. Just shoving an entire chapter in. Okay? It's awful, but that's the way we're doing it. Okay? Most of the reactions we deal with are heterolytic, meaning 2 electrons move. Okay? Questions? Make sense? Okay. Our breakdown on our rules here. We can move electrons from a bond to an atom or an atom to a bond. That's our basic motion. Okay? Particularly when looking at resonance. When we move to reactions, we can talk about other things. Okay? But we aren't there yet. Bond to atom and atom to bond. Okay? So our structure is pinned. We'll find a source of electrons. That source can be a non-bonding pair, okay, or, and I'm using the terminology here again, a multi-bond. Okay, one of the multi-bond can move. You're only moving a pair of electrons at a time. If that means more electrons have to move, so be it. Okay, but you're moving a single pair of electrons. You will move electrons into the immediate vicinity, bond to atom and atom to bond. You'll notice there's a third one on here. That's for solving the bottom one. After you've done the motion, verify your octet is satisfied. If you have too few electrons, okay, repeat step 2. Start moving some more electrons around. If you have too many electrons, you can break a multi-bond, and here's where we're bringing in another term, a pi bond, by moving electrons. Okay, and we'll look at that with this example down here. So, what can we move? Mm-hmm. Pi bond, our multi-bonds. These are the only things we got. Okay, which one? Why any of them?
Well, you want to do all 3 at the same time, so that you don't see enough time.
How do we move electrons?
Bond to atom.
Bond to atom or atom to bond? Well, right now we're starting with a bond, so we can only go bond to atom. So which of those 3 do you want to move? The upper right, I completely agree. We're going to take those electrons and I want to move them from the bond to an atom. So, ta-da! I heard reference to an exceeding of an octet. Okay. Where I believe you were referencing is actually the next step, and we'll see that in a second here. Sorry, I didn't like the way I drew that. So I want to show that lone pair to represent that it has moved, or that it has shown up in a new location. I can't represent it as a line because it's no longer a bond. I didn't touch any other part of the structure, which means everything else must be drawn the same. What do I do now? No. What do I do now?
Formal charge.
Formal charge. Always got to backtrack out to your formal charge. When we go through and assign our formal charge, we will find that the carbon with the lone pair of electrons
-1.
is a -1. Has it exceeded its octet?
No.
No, and that's where that one gets tricky. We haven't exceeded any octets yet. Okay, we may not like that because carbon has a lone pair. Carbon gets lone pairs all the time. It's irritating and obnoxious, largely in second semester. Okay? And that's where most students stop because they saw where the electrons moved. There's new things there, so it must be true that I'm done. What is the charge on this structure? -1. What is the charge on our starting structure? 0. All we have done is moved the electrons. Have we added more to the structure?
No.
No, which means the red structure is
Neutral.
currently drawn as false. We're missing something. What are we missing?
Formal charge.
What formal charge are we missing?
On the carbon.
Carbon, not positive.
that initial carbon, the one that was involved with that initial pi bond, lost electrons. Okay? We could say it started neutral. If it loses electrons, it must then become positive, so we don't have to calculate formal charge, but if we did, 4 minus the number of non-bonding electrons, 0 minus the number of bonds. We have a +1 charge. Okay? That is okay. Is that a good resonance structure? No. Why not? It has charge. So it is a higher energy structure than our starting one. If we were asked to provide resonance, that should not officially be an answer. I have all sorts of hard times with that because through the course of the semester, we will probably accept that as a valid resonance structure. Okay? Once we've drawn one resonance structure, what should we do?
Are there any other resonance structures?
Do we have more? Well, starting with that structure, what's the most reactive thing in there? Okay. We have a positive and a negative. I tend to focus more on the negative. Sounded kind of depressing in my head. The reason why I'm focusing on the negative is that organic chemistry is all about the movement of electrons. The positive charge doesn't have electrons, so I'm going to keep my focus on the negative. Okay? Depending on the system, I may be going back and forth between evaluating either one at an individual instant, but I can only pick one. So I'm going to pick the negative, and I'm going to move it. I could move it back to this bond. We're looking from an atom to a bond. The problem with that,
Doesn't give you any new information.
I just went backwards. Okay? That's fine. It works. It's allowed, but that's not useful. Not new stuff. So I'm going to try and go from an atom to a different bond. I'm going to go to this bond.
Can't be done.
Okay? We're hearing some cries out from the peanut gallery that that is a bad move. How many people are okay with that being a bad move? Okay, like 2 people and a few head shakes yes. Okay? Which means we're missing something. That's okay. Why is that a bad move? You've exceeded the octet on the hydrogen. Hydrogen can't have more than 2. So that is a bad maneuver. Oh, I'm going to get really dicey with this erasing. So I'm going to move it instead to here. Atom to bond. And I had an opportunity with the other one that I missed, so we'll take it here. What is the problem with this move? Now I've exceeded the octet on the carbon. This is where these octet things come into play. I'm not at too few electrons, I'm at too many electrons. Okay? In the case of when I had exceeded the octet for the hydrogen, I'm still in the same boat. I'm going to break a multiple bond. In the case when I had the double bond to the hydrogen, how many multiple bonds were connected to the hydrogen? Do I need to draw it again? How many multiple bonds, different multiple bonds, are connected to this hydrogen? 1. If there's only one multiple bond, I've exceeded the octet, I'm going to break that multiple bond by moving the electrons where?
Yeah, with the carbon.
To the carbon, away from the exceeded octet atom, which would thereby invalidate the move to make the pi bond anyway. Does that make sense? Same thing's going to happen here. Where have I exceeded the octet?
Top left carbon.
This carbon has exceeded the octet. So I need to break a multibond. And I'm going to break it by moving the electrons
Could you move it around the structure?
jumping ahead a little bit, away from our exceeded octet. Because we have 2 multiple bonds connected to that, I could choose either one. Which one do I want to choose, red or black? Okay, suggestion was black, so of course I'm going to say red. If we move the red, what happens?
We invalidate our movement.
We go backwards. That wasn't productive. So I agree, let's try black. We're going to move those electrons. How do we move electrons? Bond to atom. Okay? So I could say, well, I'm going to move those electrons like that, just like we did in the previous system. The problem with this is that this black structure is invalid, which means I'm not allowed to draw it. I know that those electrons need to move, but I can't show that arrow on a structure I'm not allowed to draw. Where do I show that arrow?
On that first one?
On the structure that started to push me in that direction. So that first structure gets a second arrow. The result is I can now push straight through that invalid black structure. I'm tired of freaking drawing hydrogens, so I'm going to stop. And I would end up here. Whoops. Here. Everybody get it? Hi. What we're doing is breaking down each of those bond to atom and atom to bond transitions painfully slowly. Why am I making you do this painfully slowly?
So we understand the structure.
How many of you are going to do this on your own when you go home and do the practice? You're all raising your hands now. You are full of something that is not the truth. Okay? Nobody goes through and does this. You are doing way too much extra work to painfully grind through it. And in fact, I can already see eyes glazing over through this. You're like, why are we talking about this? The reason we are talking about it is that you will draw this, but you will say it is correct. And you will draw it when? On the exam. If I don't show you this process on how we painstakingly move through it, you're going to screw it up. And you're going to screw it up when it counts the most. Because you aren't going to bother to draw the wrong things when you go home. You're only going to focus on the right things. That CH3O cation, okay, without knowing the arrangement of the atoms, it is very hard for somebody to jump to why that answer is better than any of the others. At best, what happens is you draw it out and you lucked into the correct answer, or you get it wrong. You're like, well, why am I wrong? And you look at the solutions and you go, oh, this is how it's supposed to be. You're like, I get it now. No, you don't. You know how to look up an answer. You won't have that answer on the exam. You have to be able to look at wrong stuff and decide why it's wrong. That's why online homework is beautiful. Because it gets in your face and it says that you are wrong. And it doesn't tell you why. That part sucks. That's why I'm here. Email me. Okay? Kind of makes sense? If we continue this zippity-doo-dah process through, we'll end up with a couple other structures. We got this red one and we got the purple one. Okay? Red versus purple, which one's better? Arguably neither, they're about the same. Just because I give you an absolute of yes or no doesn't mean you have to say one of those. Okay, silence works too. Black versus red. Black. Why?
There's no formal charge on it.
There's no formal charge. If we propagate out all of these resonance structures, zip through all of them, we'll end up with a couple, I think, one more ugly looking one like the purple one or the red one, depending on your perspective. And then we'll be able to zip it around. And we're just going to erase everything. Can I erase everything?
Yeah.
Cool. Yeah, that yeah sounded like I'm sick of this. Stop drawing it. Appreciate it. It's not like this is my livelihood. It's okay. I'm not judging. Sarcasm? Much? Somebody laughed. I get one. If we do this and propagated it all the way around, what we're going to end up seeing is that we would end up with this structure. Which is better, left or right? They're resonance of each other. They aren't officially the same structure. They are resonance contributors. So if you were asked to provide the resonance structures for this compound, you could go through this painful process all outlined up here. Bond to atom, atom to bond, bond to atom, atom to bond, all that fun stuff. You draw a whole bunch of intermediate resonance that you didn't like because of the charge, and eventually you would settle on this one. Right? And you'd be like, well, this is a good one. I wish there was a shortcut where I could go from that black, nice-looking one to the weird, ganky-looking one that Mike drew. Bond to bond, bond to bond, bond to bond. That's why we're allowed to move bond to bond. There's a fundamental undercurrent for why we're allowed to do those transitions. Once you recognize that's there, you're fine to move bond to bond. Okay? You have to be careful with it because it gets overused by saying, well, I know the double bond has to be here, so I'm going to move it. No. Okay? Kind of makes sense? Okay. For the sake of hybrid structures, because we'll see it with this compound every so often, well, the electrons are shared all the way around there. There's our hybrid structure. Okay, so you may see that compound drawn like that. The hexagon with the circle in between. What's the circle? The electrons moving all the way around the ring. Okay, explaining a heavy amount of resonance. Why do we use a solid, not dashed? Because it goes all the way around the ring. Okay, so envision the dotted lines going all the way around multiple times. Eventually it solidifies. Just pretend that made sense. The point of doing all these Lewis structures is really to come up with patterns. You get 5 main categories that we've sort of addressed. Boron, carbon, nitrogen, oxygen, and all of your halogens. We've got valence electrons. We know what their neutral states should look like, and we know their happy number of bonds. At the same time we know their happy number of bonds, what else do we know? Their happy number of non-bonds, okay, or non-bonding electrons. So the whole point of making you do tons of Lewis structures and playing with that is really to get you to this point and be like, ta-da, that's it. Okay? But if we just say, ta-da, that's it, you screw it up. Okay, so push you to do some Lewis, here's the ta-da, you get to decide where you are in that threshold. Okay? Because does it get worse? Yes.
What does the pink line on boron mean?
The pink line on boron is referencing something that I don't remember from the slide that I stole it from, and we shouldn't actually see it. It's a good point. I didn't actually see that. I was just trying to represent the 3 bonds. Okay, maybe it'll appear here in a second. Yeah, there we go. It does get worse because we can have positively charged versions of these structures and we can have negatively charged versions of these structures. Okay? Why is the purple line there? It's referencing that those particular structures are missing their octets. Okay? Arguably, you should never draw a structure missing its octet. There should be some way to balance it out. There are some cases where you don't have a choice, okay, and you will be missing an octet. In that case, your best Lewis structure will be bad because it doesn't have an octet. You don't have a choice. Don't worry about it. Make sense? Hi. Does the shape of the molecule change how these now electronic patterns can interact with their outside world? Yes. Yes, which then means what else do we have to evaluate? Shape. Okay. Shape is looking at valence shell electron pair repulsion theory, or our VSEPR theory. Okay. Lewis fails to describe shape. Okay. We all know that from CH4, right? Seen the basic explanations on that?
Yes.
Yeah? Okay, so we're just going to kind of jump along there. So the electrons are going to move away from each other, as far away from each other as possible. And we end up with 3 electron geometries. Okay? Notice that when we make that statement, we're referencing these as electron geometries. I'm not saying bonding electrons. I'm not saying non-bonding electrons. We're just saying electron geometries. Okay, so we get 3 primary categories. Is that true?
Yes.
No. 151 says
Well, the other 2.
there's the other 2. We can ignore the other 2 because OCHEM. Okay. We get to use that explanation a couple times. Usually in the what sucks, deal with it, it's OChem. Here's one of those cases where it's awesome, it's cool, we don't have to worry about those other two. Okay, so no trigonal pyramidal, no octahedral. Those are our 3 electron geometries. Okay? What do we have to layer on top of that? Well, sometimes we have bonding pairs of electrons and non-bonding pairs of electrons. What is the difference between a bonding pair of electrons and a non-bonding pair of electrons? Why do they take up different space?
Because a non-bonding electrons have area to float around in their orbital. A bonding pair are shared between, there's a channel, for lack of a better term.
You got the right idea. I didn't say take it from me, but you got the right idea. Where's those electrons?
That's his point.
Being shared between us. Okay, and now they're not being shared. It's now closer to that center atom. Okay, because it is now closer to that center atom, it's going to affect all the other electrons. If I extend my arm out to share, okay, there's your prize. Thank you for participating. Okay, those electrons are now shifted out a little bit further. Because they're a little bit further away, all the other groups of electrons now can move to fill that space. So we get different shapes and sizes and bond angles coming out of that as a repercussion. Really, the only place that matters is the tetrahedral geometry, and we get trigonal, pyramidal, and bent as our shapes. Yeah? Why do we really only care about tetrahedral?
Carbon has 4 bonds.
Because
It's okay.
OChem, yay. Lewis structure is all about octets. Octets means 4 groups of electrons, tetrahedral. Okay? So most of the time we're sitting in this bottom category evaluating the shapes coming out of that. Okay? So you're responsible for acknowledging those shapes and roughly bond angles, but even for that, the bond angles tend to sit largely with the electron geometries. Make sense? Okay, there you go. Lovely little table. The tutoring center has a table like this. In fact, it might even be this, because I made it. Right? With some of their advice. Notice that the bond angles over here change a little bit. Okay, why are they changing? The lone pairs changing their distance with the atom as a comparison to the bonding, which is going to change how those groups of electrons get pushed around. Okay? Real quick example, trigonal pyramidal. There's a trigonal pyramidal. My wrist is the pair of electrons. Okay? There's our 3 bonds. Okay? If we called it tetrahedral, my wrist and those fingers are all equally spaced. What happens if that is a pair of electrons? Where do those electrons go? Instead of being bonding, they're now non-bonding, which means where do they go?
Closer to this.
Closer. Which means that angle would get those electrons closer to each other. So what do these electrons do? They repel away. Which means what happens to the bond angle? The bond angle gets smaller. That's why we dropped to 107.5. Okay? It is a really weird nuance, and you'll notice that we're using a hand to do this. Okay? We have to really pull to those models to recognize that spatial representation. Okay?
Why is there a question mark?
Any guesses? Why is there a question mark?
Is that
Okay. What is the bond angle for the bent shape in trigonal planar? That is why there's a question mark. I don't know either. I just guessed. That's it. I just guessed. Okay. Valence shell electron pair repulsion theory applied. If we were to go through and draw out structures, okay, if we drew out the Lewis structure for methane, we get this. Right? If I now want to apply VSEPR to this, I want to better represent the bond angles in that structure. Like, well, that's not much of a difference. Arguably, that's because I've been drawing structures for too long and I should have made that more like a 90 degree. I'm saying this is 109.5. To get 109.5 to the next hydrogen over here, it can't be drawn in the plane of the paper. It has to be coming out at you. When something is getting closer to you, what does it appear to be doing? Getting larger. We use a wedge. Right? Because we all live in the desert and we've seen things driving down a long stretch of road where it's nice and straight and it's hot in the middle of the winter, or middle of the winter. The other one, the middle of the summer, and you look off in the distance and it gets kind of hazy, right? So that kind of fluttering and you can see the road kind of gets almost kind of dashed, like got dotted. That's because when things get really far away, they look dashed. Right? Those are the two representations that we'll use. The hydrogen going away will be dashed. The hydrogen coming at you is wedged. Completely arbitrary inventions. If you want to use a different system, that is okay, but you better tell me that you're doing it. Okay? Because it will drastically change your interpretation of structures. Okay? If we moved out to something like cyclobutane, damn it, because we haven't talked about shorthand, carbon, 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 or names. Yeah, good job, Mike. Way to go. Take my word for it, we got cyclobutane. Bute means 4, cyclo means cyclic. It's a cyclic structure. There's our 4 carbons. Every atom needs an octet, so we drop on our hydrogens all the way around. What is the bond angle in here? It wants to be 109.5. Can I possibly put 4 atoms together to get 109.5? No, which means this structure is uncomfortable. Okay? Imagine you were sitting on a thumbtack in class. What are you probably going to do? Yeah, you're going to be uncomfortable and move and adjust and try and avoid that. Okay? You might even change chairs. Butane or cyclobutane as a structure now has a different reactivity than, say, methane because the bond angles have changed. Okay? That's going to change the energetics behind it. Okay? And really, what I want to get to, almost this slide, is actually going to be the next one because it's getting at the concept that we've already kind of talked about. Our formulas are awful. We shift to structural formulas. Structural formulas are also pretty equally awful because we don't see the spatial orientation of it. Okay, we at least acknowledge that there's pieces, but we don't see how they're really connected with respect to each other. So we might jump all the way to a Lewis structure. A Lewis structure is going to show all of the atoms and bonds, including all the carbons and hydrogens. There's lots of carbons and hydrogens. The VSEPR structure is now going to layer on wedges and dashes so we can see where all those are in three-dimensional space. Line angle VSEPR. Line angle VSEPR says that's a lot of carbons. It's an organic chemistry class. I'm going to draw carbons a lot. I'm going to stop showing carbons. Every point is defined as a carbon. How many carbons have I just drawn? 2. Okay?
6.
3. Each of those points is ending at the same spot. 3 carbons. 1, 2, 3. Okay? I could also, with the VSEPR, show where all the hydrogens are. Hydrogens show up even more often than carbons. I'm not even going to specify carbons. Carbons are gone from the system, which means the big complicated structure that if you went to try and draw out that Lewis structure according to that structural formula, which you should be able to pull off and do, becomes that. You get line angle abbreviated. This is our happy space. Okay? We're figuring out that half. Oh man, I had pictures. These are our big simplifications. Okay? Pay attention to it when doing your Lewis structures. You'll need that to help out when drawing stuff out. Okay? Those will all become second nature to you fairly quickly by just doing some quick practice, because you'll get tired of drawing everything out. Okay? With that, I apologize. I talked too long.